Hello and welcome to this presentation. I'm Miles, a member of the Predictive Analytics Lab at the University of Sussex, and I'm pleased to present our paper, Null-sampling for Interpretable and Fair Representations, here at ECCV. The problem we address in this paper is learning from data which contains spurious correlations. This is the phenomenon of an attribute strongly correlating with the prediction target in the training set, not because of a true causal mechanism, but because of corruptions in the data collection process. Spurious correlations can serve as shortcuts. It is easier to learn the spurious attribute than it is to learn the proper relationship between the input and the target. While predicting the target based on the shortcut leads to good performance during training, the model fails to generalize to new environments, sometimes to catastrophic effect. A simple example is an object classifier learning to distinguish camels from cows based on whether the background is a desert or a pasture. Let's give a more concrete example using the colored MNIST dataset. In the training set, each digit class has a unique color. For example, all 2s might be pink and all 3s green. However, in the test set, colors are assigned randomly. During training, it is more efficient for the model to learn the spurious attribute color than to learn the shape of the digit. At deployment time, however, color ceases to be a perfect indicator of class, and the model fails to generalize because it never learned the correct mapping. After all, it never had to in order to minimize the training error. The solution to this problem that we present is based on learning a representation from partially labeled data. What we would like is a representation that is invariant to any attributes we deem spurious, so that we can properly learn the downstream task. We notice that this is similar to recent work in fair representation learning. There, we seek to learn a representation that is invariant to a specific protected attribute. This could be for ethical or legal reasons. What the problem of spurious correlations really corresponds to, however, is a kind of aggravated fairness problem. The target Y and the protected attribute S are very strongly correlated in the training set, or, more generally, the training data does not well represent the broader population. In extreme cases, there can be whole combinations of demographics and outcomes missing. A recent paper termed this problem residual unfairness. This work connects the problems of fair representation learning and learning in the presence of spurious correlations. Consider the case of a loan repayment system, for instance. In this system, we only observe the outcomes, namely whether or not an accepted loan applicant repaid their loan. Crucially, we only have this information for those individuals who granted a loan in the first place, in accordance with some policy. This policy itself is updated based on the observed outcomes, creating a kind of feedback loop. Our goal is to alleviate the negative aspect of this feedback loop, while making sure that only relevant information is taken into account. In our setting, achieving this goal by training directly on the training set is infeasible. The training set cannot be used to learn an invariant representation because the spurious attribute S and the prediction target Y are so strongly correlated that learning invariances with respect to S is tantamount to learning invariance to Y. To circumvent this, we instead use what we call a representative set. This representative set is drawn from either the same distribution as the test set or a superdistribution of it. While being similar to the test set, crucially, the representative set doesn't require a target label. The representation we are to learn is task agnostic. However, we assume it does have labels corresponding to the spurious attribute. This might sound like a restriction, but in practice these labels are often readily available. Census data, for instance, may provide such labels. Given this representative set, we want to learn a representation that has 3 key properties. 1, it should be invariant to a specific attribute of our choosing. And 2, it should maximally preserve all information unrelated to the chosen attribute. And 3, we should be able to understand what changes the model made in order to achieve invariance. One way of accomplishing this is to place the representation in the data domain. In order to learn an invariant representation, we first adapt the Lafter model proposed by Madras et al. We modify it so that the S invariant representations are generated in the data domain. We refer to the resulting model as CVAE. As in Lafter, the independence between the representation and S is enforced by adversarial training in the latent space ZU. To obtain a representation that is S-neutral, we replace the one-hot vector with a zero vector. We call this process null-sampling. The representation learner is trained on the representative set in the pre-training phase. The adversarial loss is balanced with a reconstruction loss. Following pre-training, we train a downstream classifier on a fully labeled training set, which has been transformed via null sampling into invariant representations in the data domain. Many attributes of interest exist on a spectrum, such as color, and cannot be encoded by a simple binary mechanism. This results in conflicts between the reconstruction loss and the adversarial loss, as ZU is forced to encode information about S for the decoder to faithfully reconstruct the input. The obvious solution to this is to take the same path that the FFVAE, flexibly fair VAE, does. Partition Z into subspaces that encode S and not S disjointly. However, is their model better suited to this approach than a VAE? The answer, in our opinion, is yes, namely invertible neural networks, INNs, and we refer to this variant of our model as CFlow. The bijectivity of INNs ensures that all information contained in the input is stored somewhere. The goal of training is to shepherd the information into the appropriate partitions. It relieves us of the burden of a reconstruction loss and from having to capture the data distribution fully. In essence, only S needs to be learned, which allows for more effective transfer learning. Like before, we enforce independence between ZU and S by training an adversarial S predictor using the representative set. Optimizing for this objective on its own, however, is not stable, and we need the latent space to conform to a fixed distribution, so that we can null sample from it. So we add a loss that maximizes the likelihood of Z with respect to a specific base density, which in our case is Gaussian. Without the log likelihood loss, the model's posterior would either collapse to a delta distribution or diverge. We start by splitting the INN's latent space into two partitions. We denote the partition in which we wish the S-relevant information to be emplaced as ZB. We denote its complement the partition in which we wish all information we are interested in keeping, that is, all that which is unrelated to S, to be emplaced as ZU. The partition size should only be as small as needed to contain all S-relevant information, as any excess dimensions will impinge on information unrelated to the undesired attribute. Thus, proper selection of the parameter is essential to getting the most out of the model. We discuss in the paper some possible approaches to tuning it. As with the VAE, we refer to the process of firstly encoding the input, secondly zeroing out ZB, and thirdly inverting the model to obtain XU, or S-invariant representation in the data domain, as null-sampling. Between the CVAE and CFlow models, the null-sampling operation remains consistent. The difference is in how the decoding is realized. Here we show both quantitative and qualitative results for colored MNIST. The sigma in the plot refers to the width of the distribution from which the colors are sampled. Our INN-based CFlow model always yields the same accuracy for the downstream classification task, regardless of sigma. For the CVAE, the accuracy decreases slightly because of the difficulty of simultaneously minimizing the adversarial loss and the reconstruction loss. Looking at the images at the bottom, on the left are the original images. In the middle are the S-invariant null samples learned by the CFlow model. On the right are their complement, the S-only null samples. We hypothesized that the INN would generalize better to out-of-distribution data, since it only has to separate out S. To corroborate this, we conducted experiments where we trained the models on a mixture of datasets from the NIST family, colored in the same fashion as colored MNIST, and then deployed in colored MNIST itself. While both the VAE and INNs learn to successfully remove obscure color information, the former does not reliably preserve semantic information. The orientation of the digits or the thickness of the strokes, for instance, are in some cases visibly altered by the null-sampling process. In extreme cases, the class of a digit as a whole is mutated. For real-world datasets like Celebi, we do not have control over the data generation process, and with it, the ability to directly synthesize varying degrees of bias, as we did with colored MNIST. Instead, we interpolate between different levels of bias by biased subsampling. The full details of this process are defined in the paper. There's a mixing parameter, eta, which controls the degree of dataset bias. For eta equals 0 and eta equals 1, y is completely determined by S. Here we show results from a downstream classifier trained on the invariant representations produced by our two models, compared to two baselines. The sensitive attribute is gender. The target is either smiling or high cheekbones. We can see that especially for the extreme eta values, our model significantly improves accuracy as well as fairness with respect to gender. We compare against a CNN baseline and the learning not to learn model designed for the same setting we consider. On the y-axis of each chart is for test accuracy, the higher the better. On the x-axis, we show the fairness of the predictions, measured in this case using demographic parity based on the absolute difference. The further to the left, the better. In an ideal world, a model would occupy the top left corner of each chart. These are the qualitative results of the CVA model. On the left are the original images. In the center, we show the S-invariant null samples, and on the right are the S-only null samples. We can see the model does an excellent job of removing gender information, although the images are a little blurry. Finally, we have the qualitative results from the INN model. These appear much sharper than the VAE-generated images. The S-only null samples are also more detailed. This allows us to see much more clearly what the network thinks the S label refers to. Upon closer examination, we can see that attributes such as makeup and hair length are also sometimes modified in the process. Some prime examples of this are framed to have red. This is due to inherent correlations between these attributes and the protected attribute gender. We can easily identify this thanks to our representation being in the data domain, a major advantage of our approach. Thank you for listening. I hope this presentation has inspired you to check out our paper.